Okay. Okay. All right. Welcome. We're glad you're here tonight and happy to be talking about, is magma real? Because most of us were taught that magma is inside the center of the earth, or the outer core of the earth. But we're going to be discussing that, which kind of relates to rocks and how they're made. Some of you came in looking at some of the rocks we had on display, and so hopefully this will kind of give you an idea, because you need to be thinking about how those rocks are made, and then also how that relates to whether there's magma inside the earth or not. And so we'll be talking about that. But we're going to kind of start with a general introduction of the universal model, a new millennial science, and that is going to be presented by Spencer Wade. So I'll turn the time over to him.
Hello. All right, so my name is Spencer Wade, as my dad said. I'm the son of the mastermind himself, so this should go pretty well. Today I'm going to be talking just an introduction about the universal model, so here we go. So what is the UM? The UM is a book that is 27 years in the making. It is a revolutionary book that changes the whole face of modern science. The purpose of the UM is to restore truth and order in science by identifying natural laws. Well, what does a natural law mean? A natural law is a statement of truth, which is pretty simple, right? You would think that the greatest scientists of all time would be trying to find truth, right? And because that's kind of what science is all about, is finding truth. So the UM actually took this book, 100 scientists who shaped world history, and kind of made a chart of, these are the time periods going back to 500 BC down to 2000. We see, observations, technologies, and theories where we're able to see where those are. For the past, what this chart kind of shows is, here we see all these times where theories either became laws or they were thrown out. They back in the day, they didn't see any point of having a theory if it couldn't be tested and experimented or made into a law. And if it wasn't able to do that, then they would just be made into, or just thrown out and not cared about anymore. So, and then here we see now there are a lot more theories, and now there's no more new laws. For this whole entire past 150 years, there's no new laws that are being made. So that just kind of shows the importance of the UM and why it's so crucial for us. So two of these theories, these are probably the most famous ones that you've probably heard about: the theory of relativity by Albert Einstein, and the theory of evolution made by Charles Darwin. So those are just two examples of those theories that have been made in the past 150 years that we've been able to see in that theory list. This presents a real puzzle because we're not able to see what laws are, and so a lot of things are skewed. This could be represented in a puzzle where this is what nature is, this is what truth and everything that is true here. And then here's modern science where, where we're cutting the puzzle pieces and we're trying to make them fit, and we're trying to skew things to make them as similar to this, but it just doesn't really match up because we're trying to mash them all together. And we're not, because of this, we're not trying to find what this is. We're just trying to make our own, scientists are trying to make their own theories work. Evolutionist Neil deGrasse Tyson said, "The good thing about science is that it's true whether or not you believe in it." This presents a huge crisis, because if we're not trying, to find new truth and new natural laws, then what is the point of science? That this presents why the is so crucial. This is why my dad said the best thing about science is you can observe, experiment, and do true science to discover the truth for yourself instead of believing what theoretical scientists tell you. In simpler words, science should stand on observation and experimental evidence that you can test. All right, so this is what we're talking about today. So what have we all been taught since childhood is in the center of the earth? Can I have some hands? Yes. Magma with an iron core. Yes. That is what we've been taught our entire lives. So if our statement is correct, that if something is correct, that we should be able to experiment it and observe something, right? And so we tried to put this theory to test. So we got a basalt rock, similar to this one, and we melted it. If it was melted, and if that theory is correct, then it would be able to melt and it would make lava, right? Well, what we found was it actually made glass. You can pass that around. That's what happened when we melted a basalt, which is a lava rock. Actually made a glassy obsidian type feel to it, and it didn't make lava at all. So we saw this as a problem in modern science, and so we actually presented a new model, which is the hydroplanet model, where we have a rock water mantle, a liquid water outer core, and a solid ice inner core, which we'll get in later presentations. This is the first experiment that is actually in the book. It's called the frictional heating model. If you've ever, rub your hands together and really, really hard like that, you can feel it, heating up, right? Well, this is where we kind of get lava. You might have the question of, well, if there's water in the earth, and where does lava come from, right? Like when the volcanoes explode and they go up, where does the lava come from if it doesn't come from inside the earth? Well, we all know that there's plates rubbing together inside the earth, tectonic plates, and when those rub against each other, it's exactly like when you're rubbing your hands together. It makes heat. And when those slips, that can create earthquakes, which makes a lot of lava. And when those rocks heat up, they melt and they make lava. This is the first experiment in the book. And this is probably the most revolutionary, which is called the hypertherm quartz growth experiment. So here we take, while I explain this, I can pass this around. This is a man-made crystal. So we can make crystal. It's not something that's formed over millions of years. This is basically what this is telling us. So this is what we did. We got this quartz crystal and we wrapped it in wire. And we put it in a oven and put it under high pressure and a lot of heat. And we put it in there for 3 days, something like that, and it doubled in size. Or actually, no, 1 day. It doubled in size in 1 day after the right temperature, the right pressure, and in water, it was able to double in size in 1 day. So we had to create a term for this because there wasn't a term for this in modern science. So we made hypertherm. A hypertherm is a hyperthermal environment in which minerals grow. So hydro, water, pressure, and thermal, which is where we get heat. So this is what the environment that is needed to make minerals and rocks and crystals like you saw. So this is just another representation of that. So the Quartz growth experiment teaches us a lot of things. It's for number one, it teaches us how rocks are made. Number two, it teaches rapid growth in the right conditions. Number three is there's new terminology in modern science, hyperthermal. Number four, pressure, which is 13,395 pounds per square inch, is 5.5 miles deep, which basically means that we can make petrified wood, fossils, we can do all that. Number five, hyperthermal environment and geothermal, a big one, is evidence of the marks of the flood, of the universal flood that we talk a lot about in the book. Sandstone, petrified wood, fossils, and dinosaur bones turned to stone 4,363 years ago during the flood. It's not happening anytime today. There is no fossils that are in the ground that are fossilizing as we speak, because there's no conditions on the earth today that have those right conditions. And it also changes geologic time and the age of the earth, and changes every field of science. The contains hundreds of new scientific discoveries across many natural science fields, and it is the largest body of new scientific discovery ever published. This is some of the universal extraordinary discoveries and claims in the Earth system, which is the book that's out right now in print. My dad's holding it up right there. Is the Arizona meteor crater is not a meteorite impact crater. Most rocks do not come from melt. Fossils can form in days. It doesn't take millions of years like most scientists teach you. Most of the Earth's sediment is not from erosion. There is no magma inside of the Earth. The Earth is a hydroplanet with an ice core, and the largest rock formation on Earth is a salt pillar. In the Living System, Volume 2, it says petrified wood and fossil shark teeth are not being formed anywhere on the Earth today. The oldest human tools are not the most primitive. Evolution is wrong. Volume 3, the Universe System, it says most of the moon's craters are not from impact. E equals mc squared is disproven. One of the most famous equations ever in science is we disprove it in Volume 3 of the Universal Model. Na plus Cl does not make salt. Modern sciences, Earth density calculations are wrong. Modern scientists have not discovered any new natural laws because they are not even looking for them. So why aren't they looking for them? This is a big question that we have. And the National Academy of Science said theories are the endpoints of science. So that's their answer to that question. Is like, we'll just look for theories and we won't look for new laws. So why will the universal model be accepted by many without coming from a university or government institution? It's because truth is independent of its origin. So what is the The is the largest collection of new scientific discovery that has ever been written. And thank you. I'll hand the time over to Alan Wade.
Actually, I'm going to invite up Michael. Michael Spencer is one of my students, and I just asked him to share a couple of ideas that he had about things that he's been learning in the universal model.
Thank you. So I'm going to talk about the Arizona impact crater. So if you go to the site, it says that it's an impact crater and it's a meteorite. And if you read some of the signs, they say that the impact was created by a 300,000 pound iron meteorite that hit the ground. But that doesn't really make sense, because if there'd be that much iron still there. But if you actually, like, the amount of iron that's actually still at the bottom of the impact crater is only like 30 tons of iron. And that's a 1,000 to 1 vaporization, which doesn't make sense, and that's just one of the different things. Also, well, I have paper. Fancy. So, when an object from space that's traveling, what they say, 40,000 miles per hour, hits the ground, even if it... Okay. So, their view on the meteorite was it was a 300,000 ton iron rock that hit the ground at 40,000 miles an hour that happened 50,000 years ago. But those numbers, they don't make sense because there's only 30 tons of iron actually in the impact crater, and if it was going 40,000 miles an hour and it hit the ground, there would be glass and melted rock that would then collect, but there's none. If you've ever been there, there's none. There's no glass, no melted rock at all, and the stuff that actually is at the bottom is limestone, which if we do an experiment with that rock right there, which is where we melt limestone, and sandstone, and after the melting, it doesn't go back to its original shape, color, anything about its original anything. So if you want to just pass that around. So we just took a blowtorch to that sandstone, and it's definitely not the same. So it doesn't make sense that a giant flaming space rock hit the ground, and it didn't do that to the ground. And also, the rock, if it were to hit the ground, would cause pieces of rock and iron to fly across the surrounding area, but all the iron is there's only the small amount of iron that actually is there is at the bottom of the crater instead of everywhere. And yeah, so yeah. So there's more in the book, but I'm not a book. So but also, so what we propose that the Arizona meteor crater is actually a hydro fountain, which is when water reaches a high temperature and then bursts out of the ground in steam. Like, I mean, just like a hydro fountain, I guess. A geyser, yeah. So, yeah. Yes, yeah. Oh, yeah. I know what you're talking about. Okay, yeah.
But instead it's funnel shape.
Which is... What?
I guess we got to say it in the microphone. So instead it's funnel shaped, right? Instead of bowl shaped, it's funnel shaped. So that indicates that it came from below and then broke out of the ground at the top. because if it came from outer space, it would hit the ground and there'd be a bowl-shaped crater or indentation. And it looks like a bowl, so of course they're going to assume that. But the problem is with the sonic waves, the testing it, they were able to image where the rocks are broken, and they're broken in a funnel shape. So, and that's in the book, so you can see the picture of the research study where they did that. Okay.
That's all I have. Okay. So, thank you.
Thanks. Let's give Michael a big hand. Thank you very much. Okay. So I always like to have some of my students come and give a little bit too. But now I'm going to get into my presentation on is magma real? And we've already kind of pointed out that this, let's see. Oh, now it's not advancing for me. Oh, okay. All right. So this is coming from the Universal Model, a new millennial science. And we've got books on the back table there. And so that's kind of where we're getting the information. And today I'm covering Chapter 5, which is the magma pseudo-theory chapter. Last month we covered the introductory chapters, and so now we're starting into the science chapters, and you're here for the first science chapter, so that's good. Let's get him one of the regular books too. There should be some in that box. Yeah. Because he picked up the summary book, and that's not going to cover the same stuff. It's not going to cover kind of. You're going to be able to follow what I'm covering if you want better in the other book, in Chapter 5. So you're welcome to borrow one of those and look at it. Okay. So is lava the same thing as magma? Because I told people that I'm talking about this today, and some of them said, well, don't you see what's happening in Hawaii? I mean, isn't that obvious that there's magma inside the center of the earth because all this lava is coming out? And so I'm going to argue that magma and lava are not exactly the same thing. So where does lava come from? That's kind of our question here. And so we're going to try to cover that. James Hutton actually was the one, he's the father of geology, and he's the one that said that there was hot, molten rock deep in the earth. And he actually said, and then two of his other theories that are prominent are the geological time, that the earth took millions and billions of years to form, and then the uniformity principle, that everything that we see today is the key to the past. And the key to the past is the key to the present, is a good way to say that uniformity principle, that the same kinds of things that were happening then are happening now. He's also known for, I got to remember to, he proposed that granite had formed from a hot molten material that solidified deep in the earth. And so I'm going to pass around this piece of granite here. And one of the things you'll notice, the white is a quartz-based crystal, like quartzite. And then there's other specks that are from, let's see, what are the components? Anyway, mind blank. But three crystal minerals that's made up of, and they couldn't have formed from a melt, right? We've shown other rocks that have been melted and it turns to a glass. But that was his idea. So again, the question, what have we been taught, is in the center of the earth since our childhood. And the thing is that this idea is taught as a fact, and yet it's not. So magma is observable and is a theory, is not observable. Magma we can't see. It's not observable, it's a theory. Lava is observable, it's a fact. And so this is what the earth, they say that this is drawn to scale over here. And so the magma planet theory says that all of this inner core is molten rock. Okay, it's magma. And there's a mantle that's made of, is it working? Okay. So the magma is that orange there near the center. So they say there's a solid iron core, and then the liquid inner core, or outer core, liquid outer core is the magma. And then the mantle is a stiffer mantle. There's some magma in there, but it's starting to cool. And then there's the rigid mantle in the asthenosphere. And the crust is made up of, the continental crust is made up of granite, and the oceanic crust is made up of basalt. And so I'll go ahead and also pass around some basalt so you can see that too. So we passed around some of the granite. It's a lighter color. And then the darker basalt that's in the oceans. Okay, so let me go ahead here. The term magma and the concept of a single dominant primary magma was introduced by G. Paulette Stroop in 1825. So this theory is really only 200 years old. And the dominant primary magma is really that theory that the entire Earth was a molten ball of magma. So that's really where we're kind of trying to draw the distinction here, because we all agree that there's lava, and so I'm going to define lava in two different ways. Extrusive lava is the molten fluid rock that is manifest on the surface of the Earth. Then intrusive lava is the molten subsurface rock that occurs within the crust of the Earth. So it's not very deep, right? It's either in or near the crust, the continental crust of the Earth. So like in the 40 miles deep, maybe. But magma goes all the way down in and around the center of the Earth. And so that is only theoretical. It's molten rock material deep within the Earth in the outer core or the mantle. Okay? So, and that's because they're saying that the entire Earth was a molten ball of magma. Okay? So that's the real question. Was it that way, and that there's still molten rock inside it, even after 4.5 billion years? Or is the lava being created in the crust of the Earth and then coming out of volcanoes? So that's where the difference is. And so we're going to try to talk about the science behind it, right? So this is showing that idea that there's magma in the core of the Earth, and there's plumes of magma that come all the way from the center of the Earth up and out the crust. Okay, so they would be saying this is what's happening in Hawaii, that the magma is coming all the way from the core. Okay, any questions about that? And that's why I think it's important that we make that distinction and we try to figure it out and see, what, is the magma coming from the core, center of the Earth, or is it just being created near the surface? You had a question?
Well, I would wonder how that inner core stays off for so dang long.
Right.
Something has to be generating the heat, because otherwise the heat would be lost.
Yeah. Exactly. Yeah, so you're saying, how does it stay hot? And there has to be some way of generating that heat. And so we're going to explore some of the theories. One of them is radioactivity. But we're going to be talking about those. Oh, you're saying that it could collapse. Oh, yeah, if it stops flowing up like that and pushing it up, maybe. Yeah. Thousands of years. How does it regenerate? Yeah. So it couldn't have just stayed hot by sitting there over those millions and billions of years. So anyway, that is what we're going to explore. So let me keep going along here. And this is a theory only about 400 years old, that the Earth is the center of the solar system. Okay? Now, I don't think any of you believe that here. And you can see over here the Sol, right there is the sun. So they're saying that it was between Venus and Mars, the sun. But if I do my job right, you're going to kind of look at that magma theory the same way that we look at this. That it's an old scientific theory that people believed in the past, but don't believe in today. Against this? I haven't put much thought to that. The best evidence against the Earth-centric theory, I think with all our space probes and stuff now, we've sent them out and we've taken lots more pictures of the whole solar system. So, yeah, and I don't have any personally, but, if you believe what's coming out of NASA, then you definitely put this aside. But, okay, so let's go on. All right. So I'm just saying theories come and go, right? And the magma theory is really only 200 years old. So I'm gonna cover each of these in turn, so I'm not going to spend time on it here. Let's just go on. Earth's innermost reaches remain in many ways mysterious as the cosmos at large, right? We have questions about the universe and how the solar system's all put together. And we also haven't really explored very deep inside the Earth, as we will see as I continue on. Magmas properly belong to the realm of theoretical petrology and cannot be examined in the field, collected, studied, or directly experimented with. Okay? And that comes from a book called Magmas and Magmatic Rocks. The wild thing is in this same book, just 2 pages later, it says, irrefutable direct evidence that materials with physical properties of magma exist within the Earth. Can you believe it? Irrefutable. Right? So that's why magma is getting taught as a fact today, and that's why we claim that it's a pseudo-theory, because we say that pseudo-theories are false theories that are taught as if they are fact. And so they need to be labeled as pseudo-theories, because otherwise we're teaching the next generation this kind of stuff, even though we're also teaching them that it can't be discovered or experimented with. The question of where the magma comes from and how it is generated is the most speculative in all of volcanology. Okay? So we agree with volcanoes, but this idea of magma is very speculative, the most speculative. But how do we think that there is magma? Okay, so with these seismic waves, and we can measure seismic waves like earthquakes. There's places all over the earth that detect when there's shaking of the earth, and that shaking or seismic waves are measured with you've seen the little charts where they've got the pen drawing on the paper that's going past it. And so it measures how big the shaking is and how hard that shaking is. So, and there's 2 different kinds. There's S waves and P waves. And you have a question?
Yeah, but another thing is, how would the magma just off those polar caps?
Yeah, you're saying how is there magma if there's polar caps? Because that's frozen ice, glaciers, and wouldn't that affect the center? Good question. It could. Yeah. Oh, and why wouldn't it melt the ice caps? Right. If there's magma in the center, then it would affect not only the tropical regions, but the magma would heat up the poles right? Which, we would say are cold because they don't get as much sun, right? But if there's a heat source in the center of the Earth, it would affect the poles equally. So that is a great question. But what we're looking at here is why science believes in the magma planet, and that's because the S waves are sound waves that only travel through solids. They do not travel through liquids. So the P waves are more of a pressure wave, like a sound wave that goes back and forth, compression, and so that will go through solid or liquid. But the S waves, or the shear waves there, they only go through solids, so that's the way to remember them. And so there's a shadow zone on the opposite side of the Earth. So if an earthquake happens up here, see, it's showing you the earthquake focus up here at the top, right there. And so the sensors right around there are detecting it first, but then it's also these other stations at other places, other locations in the Earth are detecting it, all on that side and all on this side. But this area is not detecting it, and that's because those S waves get stopped because there's a liquid outer core. And we would agree with that there is some liquid inside the Earth.
So all the way across that distance, the P waves travel to that shadow zone.
Yeah. Correct. Yeah. So we can detect those. And so we're asking the question here, is there any other known liquid inside the Earth? Does anyone know of any other liquids in the Earth? Water. That's pretty prevalent, right? Yeah? Or steam water. Yeah. Good. All right. Yeah. So, excellent. So let's keep going here. And so the lava friction model, Spencer kind of mentioned that in his presentation, but I'm going to talk about it more. So again, where does lava come from, right? And so we have this experiment where in the lava friction model where if you press your hands together, you can rub them back and forth, and if you're pressing hard, what do you feel? Some heat, yeah. Okay, so that frictional heating warms up your hands, and it can actually sometimes flake off if you do it much. You can slough off some skin cells and rub off some of the dirt, and so he calls that skin lava in the book. But we're saying that's the same kind of factor happens with earthquakes and with lava, because you have thousands of pounds of pressure pushing the continents together where you have the fault lines and the earthquakes, and with that much pressure and that much force, just slipping an inch could melt the rocks and form lava. And one of the reasons that this is important is because 200 years ago, when the magma idea was starting to, people were starting to talk about it, there were two sides. There was the volcanist that thought that there was magma inside the center of the Earth, and there's the Neptunist who thought there was water inside the center of the Earth. And so they were arguing about, which one's right, which one's wrong. And basically, the Neptunist who thought there's water inside the Earth, they couldn't come up with a good reason or a mechanism for where lava would come from. But this, we think, is a sound, logical mechanism for where lava comes from. In fact, as we look at welding nowadays, there's frictional welding where it melts the metals together in just a matter of seconds. And so we're suggesting in the frictional heat law that frictional heating produces the lava from the pressure movements in the fault planes. So anywhere there's a fault line, either between crustal boundaries this way or this way, you can have enough heat not only to send lava to the surface, but it could turn water that's in the rocks and earth to steam, and that steam can explode out and form diatremes. This is one of those funnel-shaped diatremes that Michael mentioned when he was talking about the craters. So those are some volcanic structures that I think are explained quite well using this model. You had a question?
Yeah, so there's volcanoes prevalent in some parts of the earth, and then there's other earthquakes where they're not volcanoes. Is that because there's more water and so it doesn't cause as much lava? Why is there volcanoes in certain areas like active ones and not others?
It would probably be the way that it's being heated. So the water may have a tendency to cool it, but because as the water turns to steam, that may cool it some. But but whether it's created or not would be the amount of frictional heating and where that has a place to go, right? Is it going to go up, or is it going to go sideways, or somewhere else? It may be generated and go somewhere else too. Yes. Ooh, earliest volcanic. I haven't studied into that, so I don't know what the earliest volcanic eruption is. Maybe we'll have to research that and find out. But that's a great question. Yeah. Mm-hmm. Yeah. Yeah. So this is showing the ring of fire, and the red dots or red triangles are volcanoes. The black dots are earthquakes. And so this is actually not a black line. Those are actually black dots. And if you notice, they're along the plate boundaries. So that's where most of the earthquakes are happening, and it's also where most of the volcanoes are happening. And you're exactly right that some of the areas there's no volcanoes happening, right? Especially down in those deep ocean trenches, but but that is primarily where the volcanoes are happening, is in association with the earthquakes. Okay, so they relate to each other. Yeah, you had another question. Yes. Doesn't have time to cool off, and it has time to reach the surface. Yeah. Right. So that's. Okay. Yeah. So you're saying some of that hadn't been explored earlier. Oh. Okay. I like where you're going with that. It sounds like we need to do a little more research into the historical records about volcanoes to see if we can try to collaborate and coordinate that. Yeah. Right. So we need to look at it historically as well as scientifically. You had a question?
Yeah, well, can we tell the difference between an earthquake being caused by rocks being pulled apart versus smashed together? Because it looks like to me the Pacific Rim is just going north and smashing in, and that's where you're getting that super high pressure, and then that's where the lava is
movement, but you're not getting the pressure. And so you can see it like it's going forward, or the Nazca plate is getting smashed.
Yeah, these.
And yeah,
Okay.
you can see where the movement is happening because of the volcano, which
Right.
goes right along with the universal model of pressure and vibration creates lava
Right. Yeah.
theory.
So you're saying the plates moving here are creating pressure, more pressure, and more pressure is creating more volcanoes.
Yeah,
Yeah.
think of it as a car crash.
Yeah.
The back end feels the same amount of pressure as the front, but the front's the one getting crushed.
Yeah. Very good.
Where you get where the crunch is.
Yeah, a car crash, you feel it in the front more. All right. Sounds good. Yep. Good analogy. So this is a study that was done on earthquake swarms, and they were measuring when the shaking came in relation to the lava, okay, of the volcano. And they identified 46% are the type where the earthquake definitely happens before the volcanic lava. And then 15%, they were accompanying the lava and the shaking started together. And then 39%, that kind of goes to what you said about sometimes there's earthquakes without lava being produced. And they're saying 39% of the time that happens. Okay. And we better hurry along. So earth tide. And this is saying that not only do you have ocean tides, which we're familiar with, but the land that we stand on moves up and down about 11 inches every day as the earth goes around, or as the moon goes around the earth. So I'm going to have to kind of hurry through these because otherwise I'm not going to get done in time. And the gravitational pull, this is talking about moonquake tidal evidence. There's no lava or magma to create moonquakes, but it's getting pulled, and that's creating activity on the moon. But you also have twice the pull on the Earth from the moon as you do from the sun. The sun's a lot more massive, and so has stronger pull, but it's also a lot further away. So the Earth, because it's so close, is twice of the gravitational pull that we feel from the moon as we do from the sun. And so that's why twice a day we have not only ocean tides, but earth tides. And so even the geysers in Yellowstone are affected by the solar cycles. And the earthquakes in Yellowstone are very active, and there's all those red lines or fault lines in and around Yellowstone National Park, and so there's a lot of earthquake activity which generates heat for all of the geysers that are going off. So our gravitational friction law is that frictional heating in the crust of celestial bodies is caused by gravitational pull and release of the crust by other celestial bodies, the other planets around them. And to show that even more, Io is one of the moons of Jupiter, and it is between three other larger moons, and so it's in its constant tug-of-war, getting pulled different directions, and there's a lot of earthquake, volcanic activity on Io because of all that. In fact, 100-meter solid tidal bulges from the gravitational, so their land goes up 100 meters. Okay, so on to the next point. Magma theory defies heat flow physics. You guys were kind of asking, well, how does it stay hot in there for all that long? And so one of their ideas is that the convection, that there's a current of heat that's going around inside the Earth. But when we look at the continental crust, this is what a theoretical heat flow map would look like if we were using modern science and if the entire center of the Earth was filled with this hot magma. then the continental crust would kind of act as an insulator because it's 6 times as thick, 36 kilometers, compared with the oceanic crust is only 6 kilometers. And so you would think that there would be a lot of magma heat being going up and out through the ocean because the oceanic crust is so thin. And we would think that there would be a lot less coming through the continental crust. But the actual heat flow, we have more heat coming out of the continental crust than we do from the oceanic crust. And so, again, we think that if the land masses are having these little tiny, even here in Arizona, we don't feel the earthquakes, but if the land's moving up and down 11 inches every day, we're getting some of that earthquake frictional heating even here, which affects a lot of things, and one of them is the actual heat flow. Okay, so this is showing crustal thickness over here on this side, and on that side is what the magma pseudotheory heat flow should look like based on that crustal thickness. Again, if the crust of the earth in the oceans is 6 times thinner than the continents, then the continents would be cool, like is shown with the blue. You can kind of pick out the continents there. And the oceans would be hot. But instead, this is what the actual heat flow looks like. And if you think back to that ring of fire, we weren't seeing a lot of volcanoes on those deep trenches in the ocean, but we are seeing a lot of heat in those same areas in the middles of the oceans. So there is some heat coming out. It's just not producing the magma because the crust isn't as thick. So here's the two compared side by side. This is what it should look like with magma, and that's what it actually looks like. So they really don't match up. And that's another argument against magma. So accretion theory is their theory of kind of how the earth was originally formed and their theory about where magma got started. So the mass of a planetary body increases in size by the accumulation of matter, little dust particles kind of sticking together, and which collide and adhere. The bodies in the solar system are thought to have grown in size by accretion. Okay. Yeah. So you're saying it's contrary to the law of thermodynamics. And it's also not what usually happens when things run into each other. Like one of them relates it to billiard balls that just have some gravitational attraction, so they stick together. But usually you hit billiard balls together and they fly apart. And just the ambiguity is a sign that the underlying science is uncertain. So the rubble pile hypothesis is conceptually troublesome. So these are scientists that are recognizing we got some real problems with this theory. It turns out to be surprisingly difficult for planetesimals, little tiny particles, to accrete and stick together, accrete mass during even the most gentle collisions, right? So they hit them together hard at first and they're bouncing apart. So they started hitting them together a little softer, a little slower, right? But they still couldn't get them to stick together. So they're having a big problem with that theory. They can't make it happen in the lab, and it really doesn't make sense because out in space, particles are flying really fast. Radioactive myth, you kind of brought up, well, how does that stay hot inside it? So radioactivity is one of the ways they say, and radioactive plants certainly do generate a lot of heat, along with the power and energy. There is a lot of heat there that they have to cool down, but this is not a natural environment. So they're saying that this is happening inside the center of the earth. But if that was true, then when we go to the beach, instead of wearing swimsuits and shorts, we'd have signs that say radioactive lava flow. You know, when you go to Hawaii, you'd have to stay away because that lava coming up and out of the center of the Earth would be radioactive. So that's not happening, so that doesn't make sense. So let's go on to the next reason. Quartz is not glass. Quartz is the most common mineral on the face of the Earth. It is found in nearly every geological environment and is at least a component in nearly every type of rock. And I think let me go ahead and pass a piece of quartz around, right? Quartz, I have some milky type quartz crystals, and then one that is the more traditional, more recognized quartz crystal with its characteristic point. Okay, so pass both of those around so you can look at those. So, you know, a lot of river rocks and stuff have that milky quartz in, and of course, a lot of the rocks have some kinds of crystals in them. So it's a component in nearly every type of rock. But even these river rocks, if you melt them, right, it turns to glass. Different types of rocks forming maybe different colors of glass, but they're all smooth. And that's what happens after you melt them. And so we're saying, well, if this all came from a melt, right, if the entire Earth, that's our real question, is if the entire Earth at one time was a big ball of magma, a big ball of molten rock, then we wouldn't have rocks like this. They would all look glassy. So we're just using a acetylene torch on them. So, oh, really? Okay. Yeah. I mean, we're just doing a real fine point, just putting a torch right on it for a few minutes until it. So, I'm guessing it's 600 degrees or something, but I'd have to check. I'm not even sure on that. Sorry. Yeah, it probably is in the book. I apologize. I don't know that right off. Okay, so melted rocks make glass, not quartz, right? Glass like these come from melted sand, which is silica dioxide, just like the quartz crystals. You had a comment or question? Okay. All right, think of it again.
The acetylene torch to get to 3480 degrees Celsius.
Okay, 3480. 3,480 Celsius. Oh, right. Yeah, we have more of a home version. That's why I was guessing quite a bit lower. But good, thank you. Okay, if we do not comprehend how quartz, the most common mineral in the crust of the Earth, is made, how can we explain the formation of the Earth, right? Because I passed around the granite, right? And Hutton was theorizing that granite came from magma, right? But no, it's made it, one of its components is quartz crystals. Okay? And do we have a glass moon, right? Because they theorized the moon was also a ball of magma at one time. But that means that the moon would be glassy, not powdery. And so here's the physical properties of silica dioxide, SiO2. The hardness between quartz and glass is different, 7 versus 5. The density is higher in quartz. The refraction is higher in quartz. And the thermal conductivity is 1,000 times different. Okay? So one's an insulator and one conducts electricity. Yeah.
So the difference between quartz and glass are the same
Elements, yes. They're both made of silica dioxide, but they have a different structure. The quartz is in a triangular crystals structure, very organized structure, but the glass is kind of all melted together, right? So it's just melted and moving around like a liquid, and then it hardens and dries in that unorganized manner. But crystals are extremely organized, and that's why these have that high conductivity, whereas the glass is more of an insulator. Okay, yeah.
So like when you melt and try melting the rocks, you might not have had enough of it to turn it into lava while the air was running in the core.
Okay, good. You're saying that we may not have had enough melted to consider it lava. Yeah. Okay. But we did have a section of it melted. So that is a good question, and that's something that we could research, right? And it's great that you're asking questions like that, because that shows that you're really thinking about it and saying, well, maybe there's a problem with the experiment, right? And let's find that, and let's do another experiment to rule out that potential problem. So, and you're saying air cooling it. That might be a potential problem. Okay, let me go back to that one. The piezoelectric evidence. So let's all say that together. Piezoelectric. Okay. So piezoelectric is the property that we're producing electrical power by putting pressure on particular types of stones and crystals. So quartz crystals are used to do ultrasound treatment by therapists. There's a variety of things that can be done with them, because they either apply electricity to generate the sonic waves and vibrations, or they are able to generate the electricity by putting the pressure on it. Okay? And you can actually take river rocks, and in fact, if you want to try that, I have some of these, a lot of quartz-based rocks like this. You can take and push them together really hard and then let it slip. And if you're in a dark room, that's why I decided not to do it here today, is it needs to be dark, and you'll see a little spark like that's showing, because it releases the electricity. As temperatures of approximately 573 degrees centigrade, quartz transforms, and most of the piezoelectric character is lost. So if it was heated above 573 degrees centigrade, then it loses that property, and it never goes back once it cools. So there's a boundary. So again, quartz rocks that we find all over the surface of the earth, like river rocks and stuff, haven't been melted above that point, so they were never a molten bit of magma. Okay. Yes, magnets lose that property too. I think I mentioned that later. That temperature is known as the Curie point, because any growth process, of course, must be effective below that temperature. Okay. Yep, that's right. That's actually coming up. You guys are thinking ahead. You're a sharp group here. All right, a quartz oscillator in our watches is actually using that piezoelectric effect to keep time more accurately than we can keep time with cores. Iron core evidence, so that's going right into what you guys were thinking. They're saying they're in spheres, and so that last little ball there in the very center of the Earth, they say, is an iron core. But geologists still know nothing about the composition of the core from direct observation. The iron core doesn't really work. So the UM's extraordinary claim is that the Earth's core is not made of iron. And so we'll ask some questions about, does pure iron come straight out of the ground? The stable phase of iron at the inner core conditions is unknown. We find no evidence for phases other than those long known from low pressure work. So even at high pressures, they're thinking it's not much different This is the iron phase diagram showing the temperature related to the amount of pressure. We don't have time to talk about it too much. But Earth's density is not 5.52 grams per centimeter cubed because pure iron does not exist in nature. So we can't have the Earth that heavy. A solid iron is only at low pressures. The Cavendish experiment is where they measured the mass of the Earth, but the UM does point out some problems with that experiment, and yeah, we can't reproduce it. So there's definitely some problems with that, and the UM points them out, but I don't have time to go into them today. So another extraordinary claim is that the Earth's core is made of water and ice. So we're claiming that the solid core in the center of the Earth is ice, which can be maintain its crystal structure at high pressures and low temperatures, and then the water is around that. Okay, which fits with the seismic shadow zone that we were talking about. Okay, some deep earthquake evidence. And what do earthquakes have to do with it? Okay, so the earthquake happens below the surface. There's a focus point below the surface. That's where the earthquake actually starts and happens. And then straight above that is where, on the surface of the Earth, is where they say the epicenter is, because the fault lines are usually kind of at a diagonal angle. And if they're happening deep inside the mantle like that, this is much, much deeper, even though that doesn't look very deep maybe to you. But the deep earthquakes are the cause of much controversy because they should not happen, right? According to the magma theory, if it's kind of this molten honey inside the Earth, this molten rock that's kind of partially hardened in the mantle there, it's hard to make that break like an earthquake where the rocks are breaking. Okay? Does that make sense? Okay, I'm not going to take time to read that. This is a seismograph they used to actually measure a earthquake on the other side of the Earth. So that's showing that seismic activity. So another extraordinary claim is that deep earthquakes contradict the magma pseudo-theory. That should be obvious. Okay, so now let's go into drilling evidence. Because you'd think, well, can't we just drill a hole and see if there's magma inside there? What? Oh, yeah. And they've tried to get that free infinite energy by tying into these. So the world's deepest excavation, though, only drilled 7.5 miles into the crust, which is less than 0.2%, 0.2% of the 3,959 miles to the center of the Earth. And so I tried to kind of map out how long this would be. So there's 10 miles, and that's just going across town. Like, if you've been to Gulfland Sunsplash, you know where that is on the freeway there? That's it. Oh, did you? Just today. All right. Well, that's about 7 miles from here. Okay? So not very far, right? And, yeah, by car. Okay, so now I'm going to measure from that Palm Beach, Florida airport over to the airport in Anchorage, Alaska, right? And if you'll notice, that's 3,957 miles, almost as far as halfway through the Earth, right? To get it to actually dig to the center of the Earth, that's how far you're traveling. And so the amount that we've dug into the Earth would be like, traveling across town in Florida and trying to discover and explain what's happening up here in Alaska. Okay? So we haven't quite made it there. But we thought that we could tap into that free energy by digging in Long Valley, California. Because California needs more energy. In fact, all of America needs more so they picked 22 sites, and out of these 22 sites where they thought they could drill down into the magma and then get that thermal heat energy coming out of the center of the Earth, then they picked Long Valley, California, because they said, well, that's right on top of this caldera, this where they thought there was a big molten ball of magma, and so they figured they could get down there. See, that's only 10 kilometers deep. Okay? So they thought, hey, we can drill down there. So the observed temperatures favor a model in which there is no massive magma chamber in the upper 10 kilometers. So even though they picked this as the best site to drill down in and find some magma, their temperatures say no. They're finding water, they're finding rocks, and they're finding fault lines, but they're not finding magma. And they're not finding those really high temperatures. The other two boreholes is in the KTB borehole in Germany and the Kola in Russia that went 9 and 12 kilometers respectively. Yeah.
The theory of ice being in the core,
Mm-hmm.
another reason it could work is because how otherwise do you get water from wells?
Right. Yeah. Yeah, the water table on the Earth fills up the water in our wells, so maybe there's a lot of water inside the Earth. And they are finding more and more water inside the Earth. So in the best spot, there was no magma. The deepest hole, there's no magma. And based on the temperature, there's no magma. So the textbooks may need to be rewritten. Earth's magnetic field. Somebody thought of that idea. So the magnetic field, you can put, if you notice on the right there, there's a magnet on the left, and then there's 4 different compasses, and each of those compasses are pointing towards the north on the of the magnet. So you can measure the magnetic field, and so we've kind of always pictured the Earth as having this magnetic field, and there's pictures like this in the textbooks, but the magnetic field is created by the flow. So some scientist in this New Scientist magazine is saying the magnetic field is created by the flow of the molten iron inside the core. But we already mentioned that heat would destroy that. Heat destroys magnetism. A heated iron core does not make a magnetic field. Heat annihilates a magnetic field and does not facilitate one. And in more modern times, Einstein, shortly after writing his special relativity papers in 1905, described the problem of the origin of the Earth's magnetic field as being one of the most important unsolved problems of physics. And you could see, based on those lines where they're measuring it, that it's kind of all over the place. Oh. Oh. Yeah, I messed it up. Present. Oh, let's see. If I can find my cursor. Oh, there it is. Okay. Hit present. Ooh. Okay. All right. This diagram is showing that the magnetic north is moving, and we're actually saying that it's moving even on a daily basis, kind of in an oscillating pattern. Continental uplift pseudo-theory. Again, this is a theory that the formation of the Grand Canyon is not a simple matter of the land rising with a river cutting down through it like a knife through layers of a cake. That's what the scientists are saying. And so they're suggesting that all of this was down under the ocean, and then it was lifted up to form mountains. And as it's being lifted up, the canyon's being cut through it. And this is showing horizontal movement. I think you made a comment about the horizontal movement of the plates. This is showing the magnitude of those plate movements and the direction of the plate movements. So this is real measured horizontal movement of the plates relative to each other. Okay, it's giving you the key down there. 10 centimeters per year is one of the longer lines. Okay, the horizontal position of Everest seems to be moving steadily and slightly northeastward between 6 centimeters, 2.4 inches a year, but no measurable change in the height has been measured. So, I mean, this is the tallest mountain in the earth, and we're not measuring any movement in height. No change. So where's the map? Where's the vertical plate movement map? We don't have one because there is no vertical movement of continents up and down, which is that theory of uplift and subduction, is the theory that the continents are moving up and down, and that's what's getting big mountains, and that's what's causing continents to be covered in oceans so that they can get shell fossils on the top and then they're lifted up. But that's not happening. Yes? Good point. You're absolutely right. Mount Everest is the highest peak, not actually the highest mountain, because if you go down under the ocean, there's higher ones. Right. Right. Because they've been recycled. But right, we're saying that there is no recycling. Yeah. Mauna Loa. All right. You're into science, I can tell. All right. And where are the submerged continents that are going to be lifted up later? That is another question that we're asking. Okay, other magma pseudotheories. Let's see. I'm going to write it. It doesn't really get hotter when you go inside the earth like a cave. You usually wear a coat. This one is interesting, right? This is Hawaii Islands, the theory that these magma plumes pop up. But hypothesized mantle plumes do not appear responsible for most large igneous provinces. Instead, they're very, like the island of Hawaii, instead, their very existence is questionable. No geological evidence of any kind, geochemical, petrological, thermal, topographic, requires mantle plumes. So that theory has been proven wrong, and they're stating there is no evidence to support it, but we still think there's magma. And yet that's the place where it would be most obvious, right? Hawaii, right? That's what they're pointing to as the evidence of magma, and yet they've proven it there. It doesn't work. Oh. Oh, wow. Huh. Okay, so you're saying even the satellites may be questioned because they're cartoon photos because of the temperatures. Okay. All right. Interesting. Okay. Let me go on, though, because I'm going to go on to, I want to get to the last one here, the tomographic smoking gun evidence, okay? And this is where they're taking measurements down deep inside the earth, kind of as deep as we can measure, and if there was a magma solid core, right, it would be hottest near the core where the molten magma is, right? And so with this sonic pictures, we can take pictures because it's going through something relatively solid, so we can measure those and we can see how fast they're moving, and we can create a picture using computer-aided imaging like we do with an ultrasound of a pregnant woman's uterus. We're doing the same thing here, and we can measure where it's hotter and where it's cooler. So red is hotter and blue is colder. And this is what it will look like. Do you all agree with that if magma is real? All right. So you ready to look at the real pictures? Okay. This is what they look like. Okay, let me go ahead and zoom in a little bit here. So what we have a line going across here, and along that line there's these dots, and they correspond then, in this case, with this image here. And so let's look here. 1, 2, 3 dots over. 1, 2, 3 dots over. If you notice, that's where those fault lines and earthquakes are happening, right here. And so we have the hottest areas as well as the coldest areas happening right in that boundary. Right? Right near the surface, yeah. So hottest areas definitely near the surface. Colder tending as you go down, right? And so same thing here. Second dot over, that goes to this line here. Second dot over, again, right there in Japan, where earthquakes and volcanoes happen, and there's a lot of activity with heat as well as cold. So that's where I think you were saying water may be coming in and cooling it off or something. I think water's coming in and cooling it off, but then that's why we get that explosive force too, right? Because when water turns to steam, it expands 1,700 times the volume. So it goes big, yeah. Are panda bears in Japan? They're definitely in China. I'm not sure about Japan. I'd have to check it out. I hope so. There's none? Oh, okay. All right. Good. All right. So this, I think, is pretty significant evidence because these are images based on temperatures, looking as deep into the earth as we can, and taking cross sections, and we can kind of see what's happening there. So that's a really significant image and picture, scientific measurements from these images that we've taken. You had a question or comment? Yeah. Is that this one? Yeah. Yeah, so a little deeper heat down in there. But, yeah. The hottest part is definitely up here in the surface region, right? Kind of in this area, crossing two fault lines, right? Okay. Oh, yeah, that'd be interesting. I don't know if they have or don't think so. Okay, and this kind of helps the heat flow physics make sense, right? Because if you've got those fault lines down in the bottom of the oceans. Okay, so what do you think? Is magma real? No. Yep. So we're thinking we should freeze that idea, that theory, and that there's actually ice in the center of the earth. This presentation was primarily on the pseudo-theory, and next month we're going to do another one on the rock cycle pseudo-theory, because the rock cycle is all based on magma. So, of course, it's wrong as well. And so we're covering a lot of mysteries in geology right now in this month and next month. And then after that is when we'll get into the models. And so that's where we're going to be presenting what we think is the truth, and models that are based on experimental evidence and research that can be supported. So those are the summary of evidences that we've covered today. I'm sorry it took so long. But if you want to visit Do True Science, either on Facebook or YouTube, you'll be able to see this video presentation if you want to share it with your friends on YouTube. And then I also put some of the experiments I do with my classes on Facebook in Do True Science. And I also do want to thank Darren Clough for doing our video recording today. He does an excellent job. And I do recommend, yeah, give him a hand. Thanks, good. And I do recommend that you go to universalmodel.com. If you do go to their store and decide to buy some of the books, you can get them in the back of the room here. We can sell them to you. But if you go on their website and do it, then put in the code DOTRUE, which is kind of my code that gives you a special discount. And you can share that code with your friends too, so they can get a little discount on the books and rock kits and stuff that they have there. So thank you very much. Appreciate it. And I'll take any questions that you have. Yeah. Mm-hmm. Right. Oh. Yeah. Yeah, it would. Pressing up against the edge. Um, yeah, and it would be, you would have gravity pulling it in as well as the spin flinging it out. So, yeah, gravity would be less at the poles. Oh yeah, you're talking the spin would be very different. Yeah. It'd be interesting to try to figure out a research experiment with some of those ideas, because you might be able to measure some of those differences and stuff. But you're going to enjoy the universal model, because right now this book here is volume 1, and it's all about the Earth system. And so that's just focusing on the Earth. But there is a volume 2 and volume 3. Volume 2 is about the living system, and then volume 3 is the universe system. And in that, he redefines mass and length and time, and really, yeah, it'll be really exciting. It's probably less than half done now, so it's going to take a while to get that one done. Yeah. No. So the volume 2, the Earth system, says that evolution is a pseudo theory, and then we explain a living model that is different. Yeah. And supports the historical evidence that you were talking about. With the volcanoes and stuff too. Yeah.
But, like, you know how a lot of people say when you go down deeper, it gets hotter.
Mm-hmm.
How would that be?
So, like in caves, you can go deeper and it doesn't get hotter. So, and even in mines, there's some mine shafts that may be hotter, but that's because they're closer to fault lines and earthquakes, where there's that frictional heating generating some heat. Other areas where mines where you're far away from fault lines and earthquakes, there is no real heat going deeper. Oh, Arizona crater. Michael, my student, talked about it just real briefly. We didn't go into it too much today, but we will probably as we go more into the book. they gave me to teach from said that evolution was the overarching theme of all biology. And so they kind of wove it into every single chapter of the book. And I just had a lot more fun learning from him about science like we talked about today. And it just kind of blew my mind, and yeah, it was very enlightening, and ended up being very fun to study and learn. And so I started reading it about 6 years ago, and started teaching for the author and helping him with yeah, so it was well before it was published.